Hello everyone, I am Professor Veena Joshi from the Department of Geography, Savitribai Phule, Pune University. I am a teacher of Geomorphology and I have been teaching this course, Fundamental of Geomorphology, for the past 35 years. This is a subject in which we try to understand the different processes which are responsible for the formation of different physiological features on the surface of the earth. I hope you will enjoy the lecture. In the last lecture, we talked about the continental drift theory. What we saw in that was that for the first time, Alfred Wegener put up a theory which says that all the continents were joined together and started drifting apart sometime around Mesozoic period. He had given the evidences to support his theory which were very, very convincing, but in the end he failed to give a very scientific answer to the question, what was the mechanism or driving mechanism. So we will take over from that point where Alfred Wegener left behind. We will be starting with answering this question, what was the driving mechanism, in the next lecture that we are going to do, that is plate tectonics. In this section, we will be starting with what was the mechanism which has given rise to the driving of the continents away. We will be trying to understand what is paleomagnetism, first what is geomagnetism and paleomagnetism. We will try to understand what is sea floor spreading, and then finally we will try to discuss what is the meaning of plate, how the plates move and what are the different plate boundaries. And then we will come up to the next point, what are the different features which are formed at the plate boundaries, and finally what is the association between the tectonic activity and the plate tectonics. So this is the gist of what we are going to study in this talk. So now let us start with plate tectonics theory. This animation which we see now, this animation has come a lot later after continental drift theory. Now we see a moving globe right now. What is plate tectonics or plate tectonic theory? It is a Greek word, tecton, that portends to building. Plate tectonics is a scientific theory which describes the large scale motion of the Earth's lithosphere. In order to understand the plate tectonic theory, we definitely need to go back to the geological time scale once again. Earth was formed 4.6 billion years ago. From 4.6 billion till the present, the geologists have divided it into aeon, era and the period. Aeon is the bigger division, era is little smaller division, and the period is the smallest division. From 4.6 billion till about 800 or 687 million years, we have put it under a category called Precambrian. So now if we look at the geological time scale, very roughly geological time scale is divided into Precambrian and Phanerozoic. Phanerozoic stands for the period after the fossils and the lives have come on the surface of the earth. And Paleozoic, Mesozoic and Cenozoic, these are the three periods of Phanerozoic and the divisions that we have. What is important for us is that during all these years, how was the earth behaving? Today is Holocene. The current geological period is called as Holocene, and this is how the position of continents and ocean are. This was a question which was asked to Alfred Wegener, that what was the driving mechanism. And if we move back to the flashback, in Mesozoic. And if we rotate our continents a little, they make a perfect fit. This was the Pangea that Alfred Wegener was explaining about. And he also had shown at that time that when these continents were joined together, there were flora and fauna, and we have got the evidence today in different parts of Africa, South America, Australia and India. The major milestones for continental drift theory to take its birth. The first and foremost was continental drift theory by Alfred Wegener. That had created the question whether the continents were actually joined together as one and drifted away from each other. The convectional current theory of Arthur Holmes in 1921. This also is a very, very important theory because for the first time he says that a convection current is happening beneath the crust. Wherever the heat is accumulated, there is a rising current. That rising current comes and drills through the crust and it takes the continent apart. That convection currents come down and joins a gigantic cycle, and where it comes down, the crust sinks. Then the next one is the seafloor spreading in 1960 by Harry Hess. Another important landmark was in 1961 by Robert Diaz. And finally in 1963, Vine and Matthew came up with the word continental plate tectonics theory. The sixth evidence of continental drift was already discussed in the previous lecture of continental drift, so we don't need to repeat it here again. What is seafloor spreading? Seafloor spreading and paleomagnetism is the next point. Based on paleomagnetism, continental drift or the plate tectonic theory was built on that. During the oil exploration study on the floor of Atlantic, the magnetic stripes were discovered, as how we see here in this picture, this red and a green and a blue and pink color in between the white. During this exploration, the central part of Atlantic Ocean, the middle portion is mountain, and the mountain is becoming lower and lower and it merges to the floor. The rocks are younger and younger. At the center it is the youngest. It becomes older and older as we go away from the center and as it touches the continental boundary. And also a very surprising thing was the either side of this mountain flank shows the mirror image of each other in terms of magnetism. So here we need to understand what is magnetism. We have got the North Pole and South Pole. I am not talking about the geographic North Pole, I am talking about the magnetic North Pole, which is very close to our geographic North Pole. Our Earth is like a bar magnet with a magnetic North Pole and a magnetic South Pole. The magnetic North Pole will attract all the magnetic South Pole of any substance which is there on the surface of the Earth. The magnetic South Pole will attract any magnetic North Pole of any substance which is there on the Earth, like how we see the picture over here. So this is the current position, and now we can see these arrows are showing that right now if a volcanic eruption happens, what will happen now? The rock will be formed because the volcanic eruption will erupt lava. Lava will cool down and rock will be formed, and whatever magnetic substance which are present in this lava will orient towards the existing pole. So, where the north pole is there, the south pole of this magnetic substance will be pointing towards that. Exactly the opposite will be there for the southern hemisphere. And this happens when the lava comes to a temperature which we call it as the Curie point, a threshold point. Lava has got, say, let us about 1000 or 1200 degrees Celsius. During that time, all this magnetic substance will be floating without any orientation. And then, as it starts cooling, for each of the mineral, there is a threshold Curie point. So, somewhere around 780 degrees Celsius, the iron substance will start orienting to the existing pole, and as the temperature becomes cooler and cooler, it will get fossilized. That means every eruption will have the magnetic substance pointing to the existing pole. After, say, 1000 years or 2000 years, if another eruption comes out, and that also will do the same thing. And what is very interesting here in this diagram is that these magnetic stripes are showing the positive and negative anomaly. And what is positive and negative anomaly? This north pole and south pole are flipping over the years. North pole becomes south pole and south pole become, I am talking about the magnetic property. What is north magnetic pole today will become south magnetic pole in some few hundred or few million years, and it has been happening since the day our globe has been formed or it has taken its birth. So, if today a rock is forming right now, and if our north pole is here, it will be pointing towards that. And after 2 million years, another rock is forming, and that time the pole has become south. It will also get recorded, and this is what was found. So, now here in this picture you see that north has become south and south has become north. And on the ocean floor, this has been recorded that from the central part we have got the magnetic stripes, a band of positive and a band of negative anomaly rocks are found. These rocks also becomes older and older and older as we go away from the center, and it is the mirror image of each other. This is the bathymetric maps of the world that we have. The ocean floor is having all these features, like it has got oceanic ridge, the deep trenches and the plains. It is not absolutely flat as we imagine. This is exactly what is the ocean floor. This is how it looks like. We see the mountain chain in the center of the ocean. We also see a lot of roughness everywhere and the long chain of depressions. When we map it, this is what we find. In all the central part of all the oceans that we have, Atlantic, Indian, Pacific, chain of mountain is there. And along the boundary of the continents we have got the deep trenches, and this is how we find it. So, ocean floor is not very flat as how we believed once upon a time. It has got tall mountains, it has got long trenches, it has got lots of islands, and some of these trenches are so long and they are very, very deep, and Mariana Trench is one of the, it is the deepest which is found in the Pacific Ocean. So, this paleomagnetism, Earth's magnetic field is thought to result from the different rotation speed of the outer core and the mantle. And it creates what we call it as the North Pole and the South Pole. and over the million years they flip. North pole becomes south pole and south pole becomes north pole. And this is recorded on the rocks which are formed on the continent as well as on the ocean floor. But over the continent, what happens is, because of the erosion, the data is not recorded for a very long period of time. But on the ocean floor, because there is less disturbance, the records are preserved for a longer period of time. The Earth's magnetic field completely reverses, that is, magnetic north pole moved to the geographic south pole. The needle on the magnetic compass that today would point to the north pole would point to the south pole if the magnetic field should again suddenly reverse. So, this has given rise to the geologists to understand one thing. Geologists refer to Earth's present magnetic field as being normal because for us it is normal. If we would have been born and if the scientific knowledge would have been there, say in 1 million years before, and whatever was present at that time, we could have called it normal. So for us, North Pole is normal. If North Pole becomes South Pole one day, how will we know that? This magnetic substance which I have it in my hand, or I will say that this is a magnet. When I release this magnet, it will start very freely floating and suddenly it will point to the North Pole. And as the magnetic reversal starts, this will become weaker and weaker and one day it will not point anywhere. The Earth will become absolutely without any magnetism. And that is very dangerous. That is when the asteroids comes and hits the surface of the Earth. The harmful rays from the sun, because our magnetic field is protecting our Earth from all these harmful substances. Then it will become stronger, but it will start rotating. The South Pole will start pointing here. That is how we get to know that they are flipping or reversing their position. How does it apply to plate tectonics? Then at various times in the geological past, Earth's magnetic field has completely reversed. The existence of such magnetic reversals was discovered by dating and determining the orientation of the remnant magnetism in lava flows on the land. So, like how we found those magnetic stripes on the ocean floor, they are even found on the land as well. Suppose when the lava is erupting and the rock is forming, whatever is the magnetism which was present at that time, the magnetic substance will be pointing towards it. So, over the period of time, the rocks will form one on top of other and it will be recording the negative and a positive anomaly of the magnetic substance or the magnetic pole. The same record is there on the land also, but on the land, the record is not very long, say just about some 100 million years. But here in Y or in Lonavala or in Kalsubai, the basalt that is there in Maharashtra, each one also has recorded this. The explanation of this has come up with Harry Hess. He is an American geologist. He studied the mid-oceanic ridge and he suggested that the ocean floors move like conveyor belts carrying the continent along with it. So this is how the ocean floors are moving. And this is how it looks like. The phrase sea floor spreading was coined by Robert Diaz in 1961 in Nature paper. And he explains that lava is coming from the crust and it is pushing the continents away from each other. New rock is getting formed in the center, and during this period of time, both the sites have recorded the positive and negative anomaly. So, this is a cartoon which shows that here the rock is formed. When the new lava comes, the rock has gone away from each other. So, negative and positive anomaly of the magnetic field is getting recorded, and this is exactly how it happens. When it is erupting, a positive time that has gone farther and farther away. This is also the reason why the rock is youngest in the central part, and it becomes older and older, and the oldest rock which is found on the surface of the earth is around 200 million years old. We do not have a single rock on the ocean floor which is older than 200 million years old. Whereas on the continent, we have got Precambrian 3.5, 3.6 billion year old rocks are present. In fact, the Deccan Trap over which the Maharashtra is sitting, the below base is Precambrian rock. That means this process of sea floor spreading started around 200 million years ago. The central portion of the Atlantic Ocean, what we see is the mid-oceanic ridge. This is a chain of a mountain, and it becomes lesser and lesser in the height, and it merges into the plain. It becomes older and older from the center, and it becomes oldest here, and it is along this floor that the magnetic stripes were discovered, and the geologists have got the age of all these now. The central part is the Holocene, which is the youngest, and as we go away from the center in all the ocean, whether it is Atlantic Ocean or whether it is Indian Ocean or Pacific Ocean, from the central ridge, as we go away from there, the rocks become older and older, and both the flanks are showing mirror image of each other, and the magnetic stripes are there. The diagram tells us that the oldest is somewhere around 180, 190 million years old, and the youngest one is Tudeca age. That means the sea floor spreading started not earlier than 200 million years old. If that is so, if there is spreading happening and earth is not expanding, what does it mean? Because it should expand. There is an explanation for that. From all the ocean floor, the earth is expanding continuously, and the new rock is getting formed. Ocean floor is becoming bigger and bigger, but we know that the diameter of the earth is not increasing even by 1 inch. That means somewhere, whatever is the additional rock which is getting formed in the central ridge, it is getting subducted somewhere, means it is getting consumed somewhere, and that is then another process called subduction has come. So we know that the central part of all the ocean is getting spread and new rocks are formed. It is happening in Atlantic, it is happening in Pacific or Indian. But we know that the diameter of our earth is not increasing even by 1 inch. What does it mean? That means that whatever is the rock which is getting created, that much is getting consumed somewhere, and therefore that's the reason why the globe has maintained its diameter. That is when a concept of subduction has come. That is a process by which ocean floor sinks beneath a deep oceanic trench and back into the mantle, allowing a part of the ocean floor to sink back into the mantle. That means as spreading is occurring, the slab is coming colliding with another slab and it is getting subducted into mantle and it is getting consumed there. And it is getting subducted at a zone which we call it as trench, or a trench is formed. So a deep oceanic trench occurs at the subduction zone. Deep underwater canyons form where the oceanic crust bends downwards. What are the evidence of seafloor spreading? The mid-oceanic ridges and in the center, and in the opposite side at the boundary of the continent we have got the trenches. The basaltic oceanic crust become progressively older away from the mid-oceanic ridge. Magnetic surveys show elongated patterns of normal and reverse polarity of the ocean floor in bands paralleling the rift and symmetrically distributed as mirror image on either side of it. Pillow lava. This is when lava cools in the water, it forms the pillow shape. Pillow lava is found all over the central part. This is the mid-oceanic ridge. The central part is still hot and rifting, and the whole block looks like this. So here comes back to the question, what drives it? Convection. From the core, the outer core is liquid and the inner core is solid. And from the mantle, a convection current generates. And as we see in the picture, as the convection current rises up on the top and as it touches the lithosphere, and as it moves away from each other, it breaks the continent. It goes all the way and it starts sinking at a point, and as it starts sinking, it will form a circle. That is when the slab is going to come and get subducted. So what we have seen in the previous slides, what we discussed earlier, that sea floor is spreading and it is subducting in the other end. The whole thing is driven by convection. This is Hugo in 1954. He asked, what happens at the boundary where the subduction is happening? And he discovered, he asked this question, where does the ocean crust go? This is a very self-explanatory diagram and very important for us to understand. The whole movement of sea floor spreading starts with the current, convection current, but once it starts pushing, there is another force that comes as the ridge push. So that is going to push the slab, and as it starts subducting, the weight of the slab itself becomes so heavy that it is pulling. So ridge push at the oceanic center and slab pull at the subduction is a mechanism that soon follows after this convection. Together forms the driving mechanism of plates. All these things put together has come up with what we call it as the sea floor spreading. That sea floor spreads and it subducts at the opposite end. Some of the timelines that we have: in 1967, Mackenzie and Parker; in 1968, Jason Morgan, Xavier, these are Pishin. They are all the pioneers of the formation of this theory called plate tectonics, and finally it is Frederick J. Wine. He is generally believed to have been the person who has used the term plate tectonics. So by 1960, all this patchy information about paleomagnetism, the occurrence of magnetic stripes, ocean floor, rough topography, all these things have come together, and finally we have come to the theory of plate tectonics. Javier Le-Pichon is also one of the founders of the plate tectonics. These 4, 5, 6 names are very, very well known. So what is plate tectonics? Or what is plate? A tectonic plate is an individual piece of lithosphere that moves over the asthenosphere. So a huge block. The Earth's crust is broken up into different plates. These plates right on top of the mantle or asthenosphere. Asthenosphere is the layer which is immediately below lithosphere, which is in a semi-plastic state, which is not exactly liquid, but when pressure is put into it, it liquefies and lava comes out of that. It is on this semi-plastic layer. It is like milk bag. I press like this. So we call it as ductile, that I can make shapes with that. So the plates are riding on top of this asthenosphere, and the plates are the lithospheric blocks. There are two types of plate. One is the lithospheric plate and the other is the oceanic plate. The lithospheric plate or continental plates, they are very thick, and oceanic plates are thinner. These are the names that we have. The continental plates are African plate, Antarctic plate, Eurasian plate, Indo-Australian plate, North American plate, South American plate, Pacific plate, and the Nazca plate. These are the pictures that we have. North American. So the continental plate, then smaller plates, Arabian plate, Caribbean plate, Cocos, Juan de Fuca, Philippines, Scotia, Caroline, and Fiji. They are the smaller ones. The position of these plates are shown over here. This is the picture of the central ridge. The location where two plates meet is called as the plate boundary, and the plate boundaries are commonly associated with geological events such as earthquakes. So all the plate boundaries are the areas where severe earthquakes do happen. It also creates many topographic features such as mountains, volcanoes, mid-oceanic ridges, and oceanic trenches. The dots which we see here, they are indicating the earthquake epicenters. All the subduction boundary will have a lot more intensified earthquake than the central ridge. Here I would like to make a very, very important point. We have got two, as of now, we know that a spreading is occurring. That's going to be one boundary now, where crust is getting created. There is a point where the crust is getting subducted and it is getting consumed. That is going to be another. Earthquakes happen at both, but the one which is occurred at the spreading is not very intensive. It is passive, because the force of convection is not that strong enough to give that kind of earthquake, whereas at the subduction the earthquake is immensely intensified. Why Japan is always under earthquake, and the tsunami that Indian Ocean had in 2004, 2005, they are all the subduction plate boundaries, and it shows that there is one-to-one relationship between the occurrence of volcanic activities and the earthquake and the margins. These plates move in different directions. Even if it is the whole block, each part does not have the same speed, which creates a lot of tension and breaking it up, creating smaller plate. The speed is some the highest is sometime it goes up to about 15 centimeter, but by and large 5 to 6 centimeter a year is the average rate of the movement of the plates. The mid-Atlantic ridge is the mechanism by which continents drift riding on the mantle. So, this gigantic convection current is the driving force, followed by ridge push and slab pull. The ocean crust is dense and made up of basalt, and the continental crust is less dense and made up of granite. There are three types of boundaries. The divergent or spreading boundary, which occurs in the center of the oceans. The subduction boundary, which occurs at the junction between one plate and another. And the third one is called as the transform boundary. They just slide past and they are found all along the central ridge. The three types. I'll cite three examples. The best example of the subduction, Peru-Chile Trench or Japan Trench. Spreading is the central part of any ocean, but let us take Atlantic Ocean, and this is San Andreas Fault, or I'll show some pictures and it will become very, very clear to you. So, we have got three types of plate boundary: converging or colliding, that means subduction boundary; diverging or separating boundary; and transform boundary, where the two plates will just slide past each other. No one is sliding or riding over the other. The three pictures explain the three types. So, this is how a spreading boundary is formed. Passive boundary. Earthquake happens, volcano happens, but it does not create a tsunami. It is around 4 to 5, sometimes even less than that. And this is where the crust is getting generated all along the oceanic floor. In the central part, we have got this boundary. Subduction, mainly along a boundary between a continent and ocean, where this slab is subsiding and subducting the oceanic. When the two plates come against each other, the heavier one will go down, and oceanic one is formed of basalt and it is a lot heavier and it moves down. And what happens is, as the slab is moving down, there is a time that it is heated so much that it starts melting. At the same time, the density of this melt is lighter than the surrounding asthenosphere. So, it is thrown up to form the volcanoes. So, wherever we have got the subduction, we have got this mountain chain and a trench. The best example is Peru-Chile Trench. And all along the central ridge, we have got this, that is sliding past each other. We call it as the transform fault. The best example is San Andreas Fault. So, by now the plate tectonic is explaining all these features there. This is the divergent boundary. This is how the mechanism of spreading is. Iceland is the best example, the only continent over which spreading is happening, because otherwise spreading is at the ocean floor. This is what is happening in Iceland. If I stand on this one side and another one, it will start going away from each other, maybe in the next million years. Red Sea is an example of spreading. It's going to form into a big ocean once, because this is the embryo stage of ocean floor spreading. Very clearly we can say that Africa is breaking. The Middle East is going to become separate. This is how the plate starts going away from each other and ocean is formed. So Africa is the old center of Pangea and it is still being broken apart. And then some of the interesting picture. Convergent boundary, where the leading edge of one plate dips into the asthenosphere. Like this. One is dipping below the other. And as it dips below, it will form here a deep trench, very severe earthquake, and it will throw a volcano. So the volcanic arc also will be there. Very good example of a subduction. This is how the Japan has been formed. These are the volcanic island arcs. This is Japan. Here is the trench. Why Japan is having everyday earthquake and volcano is because it is sitting right next to a trench. So there are three different types of convergence. That is continent and ocean collision, one continental plate and one oceanic plate collision. Best example is Andes. Nazca plate is going down, South American plate is riding on top, Peru-Chile trench is formed and Andes mountain is formed. This rock is called as the andesite, which is formed because of the melting of the slab. These are the pillow lavas. Ocean and continent, shallow and moderate and deep earthquake. Benioff zone is, as the slab is going down, a point comes. Below that there is no earthquake. So if we look at this picture, we see the earthquake epicenters deeper and deeper, and somewhere after a few kilometers it disappears. This whole active zone is what we call it as the Benioff zone. So this is a Benioff zone because beyond this there is no earthquake activity, because if here is a trench here, so now let us take an example. Here is a trench, okay, and this is where the severe earthquake is happening because the slab is subducting. As it subducts, after a certain distance it will stop because it will start melting. So if a trench is here, the earthquake will stop somewhere. This zone is what we call it as the Benioff zone. These are all the pictures of Benioff zone. And there is a process called ophiolite. Sometimes as the slab is subducting, a part of the oceanic slab is embedded on the opposite, and they remain for many, these are very old oceanic rocks which are embedded on the continent. They are called as the ophiolites. It forms into a correctionary prism. Continent and a continent conversion. How the Himalayas have been formed. One continental plate and another continental plate are coming and joining towards each other. But none of them will go down because they are of the same density, so they will press against each other to form a mountain, and Himalaya has been formed by the Eurasian plate and the Indian plate coming towards each other. So we can see India is coming up and it is banging and it is forming into a mountain. This is the best example of continent and continent colliding, which is giving rise to different zones in the Himalaya. And the transform boundary is, they are small boundary where two plates are just sliding past each other. The best cited example is the San Andreas fault, and it looks like this, that river suddenly starts turning, and here in this picture we see that the center here the two plates are actually sliding past each other. Here at this small point, one plate is moving towards and another is moving. Everywhere here the plates are moving past each other. We call it as the transform fault. And the long lines that we see, they are the dead transform fault, or they are called as the fractured zones. So by now, earthquakes are directly associated with the plate margins. Pacific is known as the ring of fire. There are several features which are formed, and a very important one is called as the hotspot. The hotspots are the mantle plumes. They are not necessarily occurring in the plate cup boundary. They occur in the central part or anywhere, and they are permanent feature. As the plate is moving over it, it forms into islands. And now you see the Hawaiian island, which we see is the product of the hotspot. Reunion hotspot, which is there in the Indian Ocean, was responsible for the basalt eruption which has occurred in Maharashtra, the whole of Deccan Trap. Like the animation that we see it over here, that it goes ahead, and in due course of time you have got chain of mountain. And a very good example of a hotspot form feature is the Deccan Trap of Maharashtra. These are the present day orogenic activity. We have come to an end of this lecture, so some terminology I'll just tell you. Triple junction. We are talking about now two plates coming or two plates going, but sometimes there are certain areas where three plates are coming towards each other or three plates are going away from each other, and one example is the Afar junction in Ethiopia, where the movement is such that it is creating three different plates. So this is called as the Afar junction. Here you see Arabian plate, African plate, and coming close to the Indian plate, as we can see it over here. Japan, Fossa Magna, but Japan this is different, where all are coming together. Pacific plate, Philippine plate and a Eurasian plate come, and this is where the Mount Fuji is there. World's most active tectonic zone is here at Fossa Magna center. And there is a small triple junction in the middle of Atlantic Ocean also, and one in our own Indian Ocean. At the ocean floor, we have got a spreading junction, and they are known as the different name. So now let us summarize in a nutshell what is plate tectonics theory. The earth is made up of 8 large plates and many small plates. There are two types of plates, continental plates and the oceanic plate. On the surface of the earth are tectonic plates that slowly move around the globe. Plates are made up of crust and upper mantle lithosphere. And there are three types of plate boundary: spreading, subduction, as well as transform. Volcanoes and earthquakes are closely linked to the boundaries of the tectonic plates. And we have got three types of subduction: ocean-ocean, ocean-continent, and continent-continent, and they give rise to different features. And by now, the present day distribution of continents and ocean floor topography, the distribution of earthquakes and volcanoes and mountain, they are all explained by this single theory called plate tectonics theory. So now we have got the explanation of this animation that we started it with first time. So with this, I will finish this talk, that is plate tectonics, and I'll be very happy to interact with you in future, students. Thank you. So till now we are in the tectonics, interior of the earth, plate tectonics, but in the next lecture we are going to come up on the surface of the earth. We are going to encounter with atmosphere now. There are two such agents that gives rise to the formation of the landscape. One is tectonic and one is the atmosphere. In tomorrow's lecture, we are going to start with one of the most basic atmospheric phenomenon, that is the fluvial feature or the work of river. We'll meet with that lecture next time. Thank you.